In the previous video, we have used the symmetric property of the metric tensor, and I have told you that I have discussed it in one of my previous videos. But the truth is that we haven't talked about the metric tensor, about the symmetric property of the metric tensor. So in this video, we will be exploring the symmetric property of the metric tensor, and also we will derive some tensor equations which we will be needing later on. So we won't be talking about the geodesic equation and the Einstein equivalence principle in this video. So yeah, let's begin. Now, in Cartesian coordinates, we can write our infinitesimal length squared is equals to delta mn dxm dxn. Now let's write the infinitesimal length squared in spherical coordinates. So this will be something like dr squared. Now I'm not deriving this formula. You have already learned that in your vector calculus classes. So yeah, that's dr square, then r square d theta square plus r square sine squared of theta d phi squared. Right. So as you can see, you can also do that for cylindrical coordinate. However, I'm not going there. You will see that we always have the same infinitesimal coordinate length squared, right, in all of these terms. So in any coordinate system, you will always have, say, you could have m coordinate, right? So there would be dm squared, then say you have dn squared, and blah blah blah, right? So this can be written as g of, say, ij, and then we have dxi, and then we have dxj. So our metric tensor Tij in spherical coordinates will have the components 1 r square sine square theta, and then the rest of them are just zeros. Now why is that? Well, if we use this equation and break this equation down, this would become ds squared is equals to g11 dx1 squared plus g22 dx2 squared, and then we have g33 dx3 squared, right? And the rest of the terms, say we have g12 and then dx1, and then we have dx2, and then many more terms. Well, for those terms we have, say, g12, well, g first row second column, well, the first row second column is this element right here, so that is just basically 0, right? So likewise all the other terms will be 0, and we will be left with only these 3 terms right here, which consists of g11, g22, and g33. So our infinitesimal length squared will become dx1 squared is just basically, what's our first coordinate? Well, our first coordinate is r, so this should be dr squared, and g11 is just 1, so this is dr squared, and g22 is r squared. What's our second coordinate in spherical coordinates? Well, it's theta, right? So this should be d theta squared, and then what's our third coordinate in spherical coordinates? Well, it's phi. And what's our component, g33 component? Well, it's just r squared sine squared theta, r squared sine squared theta d phi squared, right? So you can see that our g of ij can be written in terms of its components, and the components are represented by a matrix right here. So if that is the matrix for our g of ij, what will be the matrix for g of ji? Well, it will be the same thing, right? Because the components, these zeros, they don't matter at all. And if we diagonally swap our, if we write g of 1 1, say this is 1 primed, let's write it in a different line. Say this is g11. Say if we had ds squared equals to, say, g 1 primed 1 and then dx 1 squared plus dot dot dot. Well, 1 primed is, I'm just distinguishing the two ones, right? We have these two ones right here. I'm just distinguishing them one from the other. So g of 1 primed 1 is also the same as, say, g of 1 primed 1 is also the same as g of 1 1 primed, right? So this is why we are saying that the metric tensor is symmetric. Why? Because, well, I have used the primes to distinguish the coordinates, but g of 1 1 is just basically equals to g of 1 1. So the components, the g of 1 1 1 and g of 2 2, which is r squared, will always be the same in our equation, right? So if we write it as our infinitesimal length, if we write it as g of ji dx I dxj, well, it really doesn't change anything, because we know that j's and i's are summed over, so this becomes g of 1 1 dx1 squared plus g of 2 2 dx2 squared plus g of 3 3 dx3 squared. And then we have these other terms, g of 2 1 of dx2 dx1. Well, what's g of 2 1? That's simply 0, right? Second row, first column. Second row, first column, right? First column. So that component is 0. So all of the other terms will go to 0, right? That is why we can say that g of ji is just basically equals to g of ij. Now let's move on to some tensor equations. Let's say we have a basis vector e mu and then dotted with e nu, right? We have established this in one of previous videos, so this should be equals to g of mu nu, right? Now let's multiply both sides by, say, let's multiply by g of mu sigma, right? So if you multiply both sides by g of mu sigma, what happens to the left hand side? Well, we know we use the metric tensor to lower or upper our indices, so this becomes e mu dotted with e nu's, let's just use let's just multiply by nu sigma on both sides. Let's just multiply by nu sigma on both sides. So the nu's cancel out, we are left with the contravariant basis vector, and this right hand side right here, we have established this in one of our earlier videos, that this thing right here, this g mu nu, g nu sigma, would be the Kronecker delta of mu lower index and sigma upper index, right? So this is our new equation. Now let's swap these two basis vectors. We know that the dot product, we can swap the vectors in a dot product, so we can write it as E sigma dotted with E mu, that is also equals to the Kronecker delta of mu sigma, right? Now let's set sigma equals to mu. Well, what happens when we set sigma equals to mu? E sigma dotted with E sigma is equals to Kronecker delta of sigma sigma. Well, what is the Kronecker delta of sigma sigma? That's just equals to 1, right? Because the components, we know the Kronecker delta is just 1, say Kronecker delta of ij, say Kronecker delta of lower index I and upper index j. We know when I is equals to j, the Kronecker delta is 1, and when I is not equals to j, the Kronecker delta is 0. So if I is equals to j, we have 1. So if sigma is equals to sigma, that's 1, right? So that's another equation, E sigma dotted with E sigma is equals to 1, right? Now, in the previous video, we talked about the definition of Christoffel symbols. Well, what is the definition of Christoffel symbols? When we differentiate our basis vector with a coordinate, right? dxj. Was it d or was it the curly d? I forgot. Let me check. 1 second. Maybe it was d. I don't remember. Let's see. No, it was the curly d, right? So this should be curly d. So we differentiated with, say, a coordinate. That was just equals to the Christoffel symbols of mu j, bottom index mu j, and we have a k right here, ek. Now if I do the dot product on both sides, say I dot it with del E mu by del xj, let's dot with contravariant ek, mu j a ek, and then we have dotted with ek. This right here is just 1, right? We have just proved it earlier. So when we have, say, E contravariant sigma dotted with E covariant sigma, that's equals to 1 when we do the dot product of those. So what we get is just our Christoffel symbols, right? The actual symbol, Christoffel symbol here, and then that is just equals to E mu by del xj dotted with ek. Alright, that's it for today. See you in the next video.